So I want to show a little review of finding the volume of a solid of revolution using what's called the disk method. The example I'm going to look at is going to find the volume of the solid formed by revolving the graph of this curve here for x between -2 and 3. So there's a picture of it right there. Around the x-axis, and you form a solid that looks something like that. It's kind of a region of space, open-ended. But we're looking for the volume of this solid or region of space. You get revolving this curve about, here's the x-axis right here, for x between -2 and 3. Once around to form what's called a solid of revolution. Give you a little bit of a maybe better sense of exactly what's going on here. I'm going to show the taskbar so I can pull up another more pictures. Here's the actual surface that's being revolved, the curve, then bounded by x between -2 and 3, and the x-axis here is right there in this 3D picture. And so if I revolve this surface about once around the x-axis, there's the solid that you'll get. Look at it from all kinds of different points of view. If we wanted to, I can just spin the thing about there. There's the solid whose volume we're trying to calculate. And actually, the way you calculate it in calculus, give you another picture here. Here we're going to revolve again, but this time I'm going to make the solid transparent, and I'm going to at the same time revolve this little line segment here going from the curve down to the x-axis. Also revolve about the x-axis, and if I do that here, now actually I want to start from b equal to 0. Let's actually start from b equal to 0 here. And okay, there we go. There's the picture again of my solid of revolution. Filled in the ends this time. Make it transparent though, and got this cross section. And if I actually move the cross section a bit, you can see these different cross sectional. Looks like cross-sectional circles. You give them a little thickness, you have a cross-sectional disk. The idea in calculus is you can compute the volume of a cross-sectional disk, give you a little thickness, and maybe then fill the solid up with a billion of these disks, all scrunched in together, not having any space in between them. Calculate the volume of each of these billion disks, and you approximate the volume of the solid. Well, the remarkable thing about calculus is you can actually do that calculation for more than a billion or a trillion to the 1 trillionth power, literally limit as number of these cross-sectional disks approaches infinity, and you get the volume, and you can actually compute it. The way you compute it using calculus is you have something called a definite integral. There's the definite integral. You've had some calculus, you know what's going on here. Got this thing from -2 to 3, pi times. Now here's your function. Your function itself gives you the radius of a cross section. If you square that and multiply by pi, you got the area of a cross section. And if you multiply that by a little thickness, you have the volume of a cross sectional disk. And it turns out that this calculation here, using calculus, and something called an antiderivative and the fundamental theorem of calculus, actually gives you the exact volume of the solid. Look at another one of my videos. I'll justify why that worked, but it's daggum cool. I mean, calculus, everybody ought to be aware of big of calculus, because you can just do so many things with it. So many things. Stay safe.